So this podcast is going to cover 3 example problems related to determining rate laws, reaction orders, and values of the rate constant from experimental data. So I mentioned in the podcast for reaction orders that everything has to be determined through experimental data. So here's some actual experimental data that we will work with right here. Okay, the example problems I chose are all from the review sheet. So this one is question number 6 from the Kinetics review sheet, and the other 2 will also be numbered accordingly. So it says data given in the data table at 660 Kelvin for the reaction, blah, 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 blah. Ignore the temperature. The temperature is just there because remember what I said in a previous podcast that rate is dependent on temperature. So if the temperature changes, your rate and your rate constant are going to change. But for our purposes, that's never going to happen. We're never going to factor temperature into the problem. So it says, write the rate equation for the reaction. So rate equations are always written in the form of rate equals K times the concentration of your reactants raised to some exponent. We are going to sit here and use the experimental data to determine the exponent. Now you'll notice that there are 3 experiments that were run in this for this chemical reaction. And just like any good scientific experiment, what the person did is they ran it once to get it like a standard, and then they changed conditions for 2 other reactions, holding one of them constant and changing the other, and then holding it constant and changing the other. So you always have a variable and a control group. And then they measured the rate to see how the experiment changed as time went on with these different concentrations. So here's what we need to do. We need to determine the effect of one thing on the rate. So we look to see where 2 experiments are held constant for one of the reactions. Then we look to see, now that that one has been removed, we look to see how the other one changed. So when we doubled the concentration of the NO, we then look to the rate, and we notice that the rate went up by a factor of 4. Okay? So what I do to determine the reaction order is I say, okay, the change in the rate is equal to the change in the concentration raised to some power. We want to know what the x is. Well, very obviously, 2 to the second is 4, because 2 squared is 4. So therefore, my x must be 2, which means the NO has a reaction order of 2. Okay? Now I do the same thing for the O2, but I hold the NO constant. Well, you'll notice the NO stays constant between experiments 1 and experiments 3. So I look at experiment 1 to experiment 3 of the O2. And I can see that the O2 went up by a factor of 4. So the O2 changed by a factor of 4. Now this isn't happening in the chemical reaction. This is actually me performing a 3rd experiment. And when I change, I actually am changing the reaction concentration, the reactant concentration. I can see how my rate changes. And I can see that the rate also goes up by a factor of 4. So I do the same thing. Change in the rate, 4, is equal to the change in the concentration raised to an exponent. Therefore, in this case, y must be 1 because anything to the 1 is the same number. So 4 to the 1 is equal to 4. Therefore, my reaction order is 1 for the O2. So this substance is second order with respect to, this chemical reaction is second order with respect to NO, first order with respect to O2. Now it says calculate the rate constant. Calculating the rate constant is easy once you've gotten the rate law done because now all you do is you plug in data. So I always choose experiment 1. Only because it's along the top and it's the easiest set of numbers to follow. So I plug in what I know. My rate is 1.0 times 10 to the negative 4. I'm solving for K. The concentration of NO is 0.02 squared. The concentration of O2 is 0.01 to the first. Pull out my handy dandy calculator. K is equal to 1 second e to the negative 4. Divided by 0.02 squared times 0.01 to the first, and it's 25. So K is equal to 25. Now, K has units, but the problem with the K is its units will change in every reaction. So my units are always in the form of 1 over molarity times a unit of time. How do I know what time? Simple. Go to the units on the rate column. Notice it says seconds. Okay, so I put in seconds. Now the molarity has an exponent. How do I figure out the exponent on the molarity? I'm going to show you the shortcut. If you want to know the mathematical way, just ask me in class. But the shortcut is simple. Add up the exponents, your reaction orders. So 2 plus 1 is 3. Subtract 1 from that number, and that's the unit on the molarities. Okay? Very simple. So that is my K value. And no matter what, now notice it says calculate the rate constant. It didn't actually say calculate the units either, but I always include units on K even if it doesn't tell me to. Now, it says C, calculate the rate expressed in molarities per second at the instant when NO is 0.045 and O2 is 0.025. Okay, so really this is just a complicated way of saying calculate the rate with these new numbers. So I say, okay, rate is equal to K, which is 25, times my concentration of NO, which they tell me is 0.045, still squared because it doesn't change for the chemical reaction, times the O2, which is 0.025 to the first. Times 0.045. I already have the 25 in there, the K value, times 0.025. Enter is, I'm going to put this in scientific notation, so this is going to be 1.27 times 10 to the negative 3. Molarities per second. Now, they told me what unit they wanted, but if they don't, again, you just come back up to the rate column, and there's your unit already done for you. You just plug it in there next to your answer. Okay? Let's try another example. Number 7. So, here's the reaction. Again, I'm just ignoring the temperature. Here's my chemical data. Now, they gave me more to work with this time, but it doesn't change the process. So, I still write this as rate equals K times the concentration of NO times the concentration of H2. Now, here's the thing. Remember, I'm the person who says, write down your formula, plug in what you know. In kinetics, if you can't remember how to determine the reaction order, all you need to do is write down a rate law and do everything else based on that rate law. If you mess up with a rate law, who cares? Because you get the rest of your work done. So if you can remember how to calculate K, can remember how to calculate the rate, just write down any rate law, even if you don't have the right reaction orders, because you'll still get most of your points. Okay? So keep that in mind. Just like plugging numbers into a formula. You may not remember what the formula is exactly, but if you plug in the numbers into the spots of the formula you wrote down, then you're going to be right. Okay, so now I'm going to determine the reaction orders. So H2 is being held constant from experiments 1 to experiment 2. So I'm going to look there. I can see that my concentration was halved. So I look at my rate law, and I say, okay, I can't really figure out those numbers off the top of my head. So worst case scenario is calculate them. So I always take the second experiment divided by the first experiment. 0.0339 divided by 0.136. And I get 0.25, okay? Well, I know 0.25 is the same thing as a fourth. So I'm going to say this is a fourth. So I look at this and I say, okay, the change in the rate is equal to the change in the concentration raised to an exponent. X must be 2, because I know 2 squared is 4. So my NO has a reaction order of 2. Now I hold NO constant between experiments 2 and 3, and I look to see how my concentration changes. So this is a doubling. This is also a doubling, okay? Because I can see it goes from about 3 to about 6. It's approximately. It might be a little bit off. And so 2 to the 2 is obviously to the first. So that's my rate equation. Calculate the rate constant. Okay, so rate constant, simple. Plug in everything in the first experiment. 0.136 is equal to K times 0.420 squared times 0.122 to the first. So I take 0.136 divided by, parentheses, 0.420 squared times 0.122, and I get 6.32. Again, my units are 1 over molarity times the time, which in this case is seconds, and I take my exponents. 2 plus 1 is equal to 3. Subtract 1, and I get 2. So my molarity is squared again. It's always 1 less than the overall reaction order. My overall reaction order is 3, so therefore my exponent is a 2. Find the rate of appearance of N2 at the instant when NO is 0.550, H2 is 0.199. Nice and simple. Find the rate, it says. Rate equals K, 6.32 times 0.550 squared times 0.199 to the first. My rate is obviously going to be something I have no idea, but I have to calculate it. So times 0.550 squared times 0.19999, there we go, is 0.380 molarities per second. Again, go back here to the top, to the formula, to the rate column, and it tells you the units. Okay. Notice that very typically, everything will be in the exact same number of sig figs. So you can see it's 3 sig figs all the way down this column, all the way this column, and this column. So I'm just going to keep 3 sig figs in my final answer. Okay, let's do one more. Whoa, there's a lot of stuff going on in here, but it doesn't change the problem. So this is number 17. It says, write the rate equation, determine the reaction order with respect to each reactant. That's a little bit weird of wording. I'll talk about that one in a second. And then it says, calculate the rate constant. So, again, how I do it doesn't change. I find 2 experiments that are being held constant, and I look to see how the other thing changes. So NO2 is doubled from experiments 1 to 2. I look at the rate, and I could see the rate is doubled as well. So for part A, I always start off by writing this first before I do any other work. Concentration of CO, concentration of NO2, and this is NO2 is going to be to the first. Now I look at the other one. Now the CO, I've got 3 experiments. I've got 1, 4, and 5 that I can use. Now you look at 4 and 5, and the difference between them is a multiplication of actually this. It's not going to look right, but it's 3 halves. And I don't like working with funky numbers. I like working with nice whole numbers. Now you notice something happened. It went from a -4 to a -3, which means they got complicated on you. Don't freak out about changing exponents. Just convert them to the same exponent. So 5.1 times 10 to the negative 4 is the same thing as 0.51 times 10 to the negative 3. Well, if I look at this, 0.5 and 1, if I compare those 2 experiments, that's just a doubling. Simple. Okay? So now I compare the rates. Oh, look at that. Also a doubling. So CO is also first order here. Now B, it says determine the reaction order with respect to each reactant. Well, didn't I just do that? Yes, I did. You're absolutely right by thinking that. But I have to write it out in the form they want it. So what they mean to say is you just look at your exponent and you say this is first order with respect, you have to say the with respect part, to CO, and it is first order with respect to NO2. Obviously, if it was a 2, then it'd be second order. A 3, third order, so on and so forth. And then part C says calculate the rate constant. So I'm looking for K. Plug in everything in the first reaction, first experiment. 3.4 times 10 to the negative 8 is equal to K times, you can use either the number that they started with or the number you changed to. It doesn't matter. To the first times NO2, which is 0.35 times 10 to the negative 4 to the first as well. Again, it's chemistry. You don't have to write the ones if you don't want to. So I get rid of all this garbage that's there. 3.4 second e to the negative 8 divided by 5.1 second e to the negative 4 times 0.35 second e to the negative 4. Enter. Oops, what did I do? Oops, I hit the wrong button. There we go. And I come at 1.90. 1 over molarities times, when I look at my time, ooh, it's hours this time, H. So, the exponent on the molarity. My reaction orders are 1 plus 1, which is 2. Subtract 1 from it, which is 1, which means my molarity would just have a 1 as my exponent. And that's how to calculate reaction orders, rate laws, and I've done everything here. Rate constants from experimental data.